It gives me still a great deal of pleasure to introduce Ray. It's a very durable pleasure because I've known Ray for quite a few years in connection with the Theosophical Society and also at one stage the Friends of the Medical and Scientific Network in Auckland,
Yeah, that's right.
which is linked with the SMN in England. But he has an extremely interesting background. As it explains here, he's made a study of cycles in a career which began with computers and programming and making mathematical models, which is a great beginning for the work he's been doing since. Investigating harmonics theory, which is a fundamental theory of the universe based on a single axiom, which I hope we're going to hear today. Very good indeed. Which has been applied in a lot of different fields as diverse as cosmology, astronomy, physics, biology, geology, climate, weather, markets, economics, history, and more. I notice there's no politics there.
Yeah.
You running it. He's actually spoken on these topics around the world in a variety of countries, and also is active in different internet forums. He began to practice Vipassana meditation at the age of 50, and I know Ray is a very ardent and enthusiastic meditator. And to me, he carries that twinkling, sparkly quality which to me, every time as a person who has survived more than one Vipassana meditation. So please welcome Ray. Give him a great hand.
Thank you very much, Ray. So my topic today is the ether underpins science and spirituality. We're going to sort of take a journey that's going to probably not start anywhere near there, but it's going to slowly meander into that. And so that's my name, and that's Cycles Research Institute, and that's our websites, if you want to look at those at all. If you search those keywords, you'll find them. The part where I really got interested in cycles, I'd had some interest in it before, but in 1977 I was doing some computer analysis for an institution or a company. They wanted to do predictions of what was going to happen in economic conditions so they could make some business decisions. And I collected a lot of data, and I decided I wanted to go a bit wider in the economy, and I got demographics and a few other things, and I put them all in the computer, and I used a thing called factor analysis. And what that does is it looks for common trends amongst a lot of variables. It will find, first of all, the strongest factor that has the most relationship to other things, and then the next, and then the next. And it came out with these 9 factors. I hope you can see them there. And you can see there's a couple, the first couple, this is ranging from 1920-something through to 1977 when I did it. The first couple are very slow-moving ones. We'll come back to them. The next 2 have both got about a 4-year cycle, and they're 90 degrees out of phase, so they're uncorrelated. Each of these is uncorrelated with the others. And then you'll see one factor 6 there, which is a 3-year cycle. And I thought, 3 years, 4 years, that sounds like New Zealand elections and American elections, they're probably the ones that affect us most. But it turns out there's more than that to it, because I found some data on the world economy, and the 2 that were 4-year ones were actually tied to things in the world economy. Trying to remember what they were. A couple of aspects of the world economy, the world money supply and something else, the world growth in GDP or something. It was world conditions. So what we were seeing in New Zealand didn't originate in New Zealand, it was all arriving here. So having accidentally found some cyclical looking things in there, I thought I'd better start actually looking for cycles and see what I find. So I took those variables that I put into there, and I slowly varied the period of cycles I was looking for, and see how strong were the cycles I found in there. And I got these 4 peaks, which I've labelled as 4.45 years, 5.9, 7.15 and 9 years. And initially I thought that's okay, and I studied each of those, and I could make a graph of what each of those was doing, and it turned out you can make predictions for 3 or 4 or 5 years ahead reasonably good. Then it started to get not very good after that. Then one day I noticed that if I multiplied that one by 4, that one by 5, that one by 6 and that one by 8, they all came very close to 35.6 years. And I thought, what's so special about 35.6 years? And it was a little while before I realised what 4, 5, 6, 8 are. If you play C, E, G, C on the piano, That's the frequencies they have, right? It's a major chord. That's playing a major chord in the New Zealand economy. And then I thought, if you couldn't do these ones, there was a hint of some smaller cycles there, but only had annual data, so I couldn't look at those. So then I got some weekly wheat prices for a long period, and I analysed those. And they didn't just have the major chord in, they had several octaves of all the white notes, plus 2 black notes in each octave. It was as if someone had sat on the piano keyboard, the sound it would make from that's what the chord prices were doing. And I thought, where's that coming from, you know? It's so strange. And then I remembered that around that time, there was a lot of studies of stuff like the Mandelbrot set, which were based on nonlinear systems. And when you had a very, very simple equation, the Mandelbrot set, it generated this really complicated, interesting thing. So I started to think about nonlinear systems. And with the corn prices, something that came up was wheat or corn, whichever one it was, wheat. It had a cycle of 5.54 years in it. And the sunspot cycle had a cycle of 11.08 years. It was exactly double. So I thought something's going on here. And we've got, this one's hard to say, but it looks like it's double that one. And those ratios in there are musical ratios. And when Pythagoras did his thing, he had lots of ratios of 2 and some of 3 to make all the notes. So that it seemed that this business of being able to make a ratio 2 cycle, that would be an explanation of something. So I had a thought about that, and it went like this. If you were growing wheat in a place where, on average, the conditions were right, but the sun was causing some change in climate to go a little bit too much, whether it's rainfall or temperature or something else, it doesn't matter. It makes it go too much, come back to the right condition, too little, back to the right condition. If it does that in 11 years, then if we're in optimum conditions at this point, then we're going to go to less than optimum conditions, back to optimum, less than optimum, back to optimum. So we get 2 cycles in the optimum conditions of the growing of the wheat. So from an 11-year cycle in the sunspots, we produce a 5.5-year cycle in wheat. So then I understood if I had a nonlinear relationship, it could make this pattern. And then I began to think further about that. Before we go to that, I'm going to show you a couple of other graphs to show you the variety of things. It was a little while before I found out about a place called the Foundation for the Study of Cycles. But then I visited them, and I found that I was walking down a path that some people had gone down before for some of it. So it's a little hard to see, that one blue one. This is actually from 1705 to 1979, British stock prices. Now it's had the long-term trend removed and is slightly smooth, but you can see it does a fairly regular cycle, which turns out to be 8.9 years, which was one of my peaks. In fact, it's exactly double the 4.45-year period one I found. So we've got another case of a cycle that's twice as long as another one. Sometimes a lot of different things have the same cycle in them. This particular one is a 9.6-year cycle. The Canadian lynx data actually they've actually got over 2 centuries of that. And the population of the Canadian lynx multiplies by 10 roughly, divided by 10 in 9.6 years, and then it just keeps on repeating that. It doesn't always go to exactly the same height or exactly the same depth, but that's the general trend of it. And at one time they found there was a thing called a snowshoe rabbit that they like to eat, and they thought it was a predator-prey relationship, and there may be some element of that in it, but it turns out that salmon in the Atlantic and tent caterpillars in America have the same cycle, they're synchronised. And ozone did as well. Excuse me. So the ozone one might give us a clue, maybe something's going on in natural things that are affecting that. It doesn't seem like that should cause such big effects, but there's a lot of animal populations that have this sort of thing going on. There was a conference in 1925 where a whole bunch of North American scientists got together and compared notes, and they found that this was one of the ones they found, but there's a bunch of other periods of cycles that appear in many different things. And so they thought they should do this more often, but they forgot to do it for a while. And then a fellow called Edward Dewey, who who was a very good economist at university, got given a job when he went to work with the president at the time, said, I want to know why this 1929 crash occurred. So he went and asked 100 economists, and he got 100 different answers. And the one that he believed was the one that said, Edward, we really don't know. If they had known, they would have been able to predict it, wouldn't they? And they didn't. So then someone else told them, don't try and work out why it happens, try and work out what happens. So he started to do that. And when he went back in the older data, he found he could find these cycles. And when he combined all the different cycles that were happening together, it predicted a crash in 1929. The funny thing is, I didn't know about this, but in 1985, I was doing the same thing with cycles, and I predicted a crash, 1985, 1996, I was predicting a crash in 1987. Later on, Dewey died in the 1970s. I got his cycles that he published in the 1960s of the stock markets, and I ran them forwards, so it had to run forwards over 20 years, and it predicted the 1987 crash as well. So that was quite surprising. Now we have short-term cycles and long-term cycles. The black and white up the top there is the magnetic reversals of the Earth magnetic field. Sometimes the poles decide to go the other way around. It's possible that we're heading towards one of those now. The magnetic field's getting weaker. That's a period of 80 million years, running from right to left. There's probably a little bit of details missing, but the general idea of that's fairly well known. And they say it's not cyclical. But in fact, there are some cycles present in it. There's some more things there as well. But you'll see the little orange marks I put up there. They're at an interval of 1.11 billion years. And you can see they quite often tie up either with a black bar or with a couple of close together black bars. And then the green ones over there, they're at an interval of 9 million years. And you can see that there tend to be more dark ones around those and more white ones in between. So there are some cycles present in that. And those cycle periods are interesting because they do pop up in other things as well. This is a long-term climate change. Now, for some reason, people that do this stuff don't realise that time's supposed to run that way. They do time running this way. So that's 542 million years ago through to the present time. And we can see that these are, the blue periods are glacial periods. In between those, you can't have ice ages. During the glacial periods, you can have ice ages, and you have them for a while. And we're at the moment just popped out of an ice age for a wee while. When we say a wee while, about 10,000 years or so far. At some point, we will probably pop back into one again. And you can see that the temperature, they measure it by oxygenating isotope. The temperature, the blue curve is the temperature, and I put there a regular cycle of 146.5 million years for comparison. And it's not throwing that exactly, but you can see that there's the deep troughs at the right times.
Is that the green?
The green one, yes. And then the green dots I've done at 36.7 million years, which is a quarter of the other one. And you can see that there's a trough, a smaller trough in the blue one at those intervals. They're not perfectly regular. You can see there's a little bit of variation, but it's got something's going on around about there. I came across a book in my studies. I used to go to the university library a lot and try and read every book on everything to do with cycles. And there was a book called Megacycles, which was the proceedings of a geological conference. And the chairman of that, the editor of the book, George Williams. I thought you might know him.
My roommate.
Is he? Oh, great. Yeah. And so in that one, it mentioned that there are these long-term geological cycles, and it mentioned about 600 million years, about 300 million, about 150 million, then 74 million and 37 million. And so here we're seeing this about 37 million one, and also the one that he said about 150 million. So we notice with these that each of them is half of the preceding one. So this pattern of halving, which I mentioned earlier, and it turns up a lot in the cycles, it turns up in everything from these very long cycles down to very short cycles, patterns of halving and sometimes thirds and occasionally other things, or factors of 2 and 3, so we'll get 6 or 12 or 4/3 or 3/2, musical ratios. This one here, we've got time running this way this time, just for a change. This is the rate of extinction of species, and each one of these black lines is from some different group of things they studied. So you can see they all do something fairly similar. Something's going on, and there are these points, which we call mass extinctions when they get really high, but you can see the rate of extinctions going up and down all the time. I've put a set of marks up there. The red ones are 26.65 million years. Now, the first reports of mass extinction cycles were for 27 million years, or sometimes they said 26. Analysing the data, I get that that's probably about the best period, 26.65 million. And the green one is 36.64 million, which corresponds to the 36.7 million I had in the other one, my best estimate of that. And you can see the peaks tend to follow those, one or the other. But I've put the blue little triangles in where the two of them come into the same phase. And you can see when the two come into the same phase, you get extra big peaks there. Now, if we're going to say that these things are caused by meteorites, and I'm not saying these big meteorites don't fall, we've got to have an explanation. One explanation is that the Earth goes through the plane of the galaxy. It doesn't do an ellipse like the planets do around the Sun, because the matter of the galaxy is much more spread out, and it tends to go around like this. And the period of one full up and down is estimated to be about 62 million years. So it would be about 31 million years each time, which is not either of those, and so it's not quite easy to understand that. But we could understand that when we go through the plane of the galaxy, there's a lot more matter there, so a lot more stuff would get attracted into the Sun and would fall down on the Earth as meteorites and things at those times. The phase of it's not right, and a few other things are not right, but it's one of the better theories, but no one's really worked out exactly why it happens. It's a little bit of a mystery, but there's no doubt that these periods are present in this record. Right there.
No, you push the bottom right. So push it again.
Push the bottom right.
The bottom right. That's it.
Oh, okay. So at one stage I was thinking about this non-linear system, so I was trying to work out how it all worked. And I was going with, I mentioned politics there, someone mentioned that, I'm not supposed to mention it. I've got all these different things that human activity have. Getting towards the top, I've got more to do with crops and plant growth and things like that. And then I've got that being affected by things that happen on Earth, sea temperature, ocean currents and all this sort of thing, and clouds and rainfall and all that. And then I put over here that the sun has some effect on this, and so does the moon. The moon's orbit, the moon makes tides in the oceans, but it also makes tides in the atmosphere, and its orbit gets more inclined and less inclined from the direction of the sun, and that affects how strong the tides get and other things. And that will pop up. So all of this was trying to explain that. And if we have many steps in a process, well, I knew that you could make harmonics like the second or third harmonic just with one step. But I saw that there were actually a lot more complicated ones there to make those other whole musical scale. So I wanted a reason why there would be harmonics of harmonics. And so this was my first attempt at that. And then I decided in the end it's actually more direct than that. And this is the conclusion I eventually came to. The universe consists of a standing wave which develops harmonically related waves, and each of these does the same. So let's explain that. A standing wave, we imagine, my preferred method of thinking about the universe is it's a big blob of ether. It's actually solid. And it's been set in vibration. We can't ask why, we don't know. But it's vibrating. You can think of it instead as being electromagnetic waves if you want. It's exactly equivalent, it's mathematically equivalent, you can translate between the two. Now, why does it develop harmonically related waves? It's a non-linear system. Now, if you look up in some physics books, they'll tell you that electromagnetic waves are linear. And that can't possibly be true, because the definition of linear is that when you get two waves coming through each other, when it's linear, they don't interfere with each other. And so a wave will go on indefinitely through the universe. Now the fact is that when a wave comes in our eye, we see it. And that's proof of interaction. And that's proof of non-linearity. But in the wide open universe out there, so many of the waves are so weak, the interaction is incredibly small and it's not detectable. But when it gets in our eyeball, the interaction is stronger because it's in the presence of matter, which is in my opinion, a very strong standing wave of electromagnetism. So that's why it makes harmonics. So every wave that starts off, if you've got a guitar and you pluck it not right in the middle, if you pluck it in the middle, it does this sort of thing. But if it's somewhere different, as well as making this mode, it can also do the second harmonic and the third harmonic, and I can't do much more than that with my arms. I'm not one of those fellas. And so you get this. So you get this effect of harmonics being made from the non-linearity. If you've got something that's affecting something else, and we can draw a graph. We can draw any shape we want here. X affects Y, and we draw that shape. If we feed a sine wave into this, the wave we get out can be decomposed into a series of sine waves that are all exact multiples of the original frequency. And that's standard mathematics understanding. So it doesn't matter what the shape is that will happen, but in particular, if you use things like an exponential one or a log curve, then the waves that we made are very strong at the start and then gradually get weaker. I'll come to that in a moment. So this is the starting point. But physics commonly has this harmonically developed waves from things. It's very common, musical instruments and other things that the harmonics are made. What's unique about what I've said here is, and each of these does the same. So this is what makes it the harmonics theory, that harmonically made waves also produce harmonically made waves. Now, it won't happen in a one-dimensional thing like a guitar or a violin. It will happen in a three-dimensional system because you get a compounding effect in each of the three dimensions. And that compounding effect makes that wave become a unique and important thing in its own right that then begins to develop its own harmonics. So this is the calculations that I do. I say each wave, so we start with the number one wave, it's got a cycle, it's got a frequency of 1. It might be 1 in every so many billion years. Doesn't matter what it is, it's 1. And it will generate harmonics 2, 3, 4, 5, 6, and each of these does the same. So we take the number 2 down and we do its harmonics. And the harmonics of 2 are 4, 6, 8, 10, 12, 14. Just the multiples. 3 does the same, 6, 9, 12, 4 does the same, 5, 6. And what we notice is some numbers like 12 pop up a lot of times, whereas 11 and 13 only pop up once. So the 12th harmonic is a very strong harmonic. It gets more energy through this process. That's not quite the finish because I just put 4 in there once, but 4 actually came out twice. So what I do now is I go a little bit further, and as I total the numbers up here, and when I get 2 things out of 4, when I feed it back in, I do 2 of each of those, and when I get 3 out of the 6, I put 3 back in there. And when we do that, we find the 12th harmonic can be produced in 8 ways, whereas 11 and 13 are just 1, and so we've got these different numbers. So I've just done a small number there. Now there's one other factor that's happening. I mentioned that if you use one of these curves, the strongest harmonic, the lower order harmonics are made more stronger, and the higher order ones weaker. And I don't know exactly what the formula for this is, but I assume that it's of the form 1 over the frequency to some power. It doesn't matter what that power is. The calculation I use works exactly the same in any case. In this case, I've shown here 1 over the harmonic number, or 1 over the harmonic number squared. So that's just showing as you go to higher order harmonics how the power drops off. And those are possibilities. It's probably just one of those or something similar to that. Now I showed you the calculation up to 12 or so. This is a calculation up to 100 of how many ways each harmonic can be produced. And when we look at this area, 48, 60, 72, 96, if we divide those by 12, we get 4, 5, 6, 8, which is exactly the proportions I got in my 4 economic cycles. So this seemed to be very promising. It was making the thing, it was making a major chord, and it was doing what we were looking for it to do. I then combined that one, which was increasing many ways to make a harmonic, with the decreasing effect of going to higher harmonics, getting less power. And so I end up with this one where it's more or less horizontal. You've still got the same thing, 48, 60, 72, 96 showing up. But there's a few other ones that are just a little bit weaker than those. So we have a little look at those. And it turns out that here's my do, re, mi, fa, sol, la, ti, do. And the mi flat and the T flat, I don't know what they're called, but the 2 black notes. So this produced exactly the strong ones that I was finding in the wheat prices. So this looked very promising as an explanation for some of the things that were being observed. That's up to 100. Then I did the calculation. This was starting a long time ago when computers were much smaller, much slower. So I do up to 10 to the power of 10, then 10 to the power of 20, and 10 to the power of 30. Every time I got a new generation computer, I'd run it a bit further, and eventually I'm overdue to do another one, incidentally. This one goes up to 10 to the 50 something. I've done it in 3 lines. This is up to 10 to the 18, then 36, and then 50 something. And you can see that the effect is that the background ones make this big black thing. There's just a huge amount of what we could just describe as noise throughout. Then we can see these ones that stand out above the others, and we can see that there's a sort of a wave happening on the top of those. And we can also look at more detail on specific areas, but at every place in that there are musical proportions. Sometimes it's a major scale, sometimes it's a minor scale, but there's more or less musical scales everywhere. And now I'm going to look at the shape of the top of that. So that's just showing the very strongest harmonics, which I call the main line harmonics. I just go 1, 2, 4, 12. I'm each time multiplying by a prime, by 2, by 2, by 3, and so on. And I put the numbers up the top there of what we multiply each time. If you can, I don't know if you can read those. It goes 2, 2, 3, 2, 2, 3, 2, 5, 2, 3, 2, 2, 2, 3, 2, 7, 2. There's a lot of 2s, quite a lot of 3s, the odd 5, occasional 7, sometimes another one 11 or 13 or 17. Now, the important thing here is I've numbered some peaks there, 1, 2, 3, 4, 5, 6, 7, 8. They're roughly, this is a log scale. This is up to 10 to the power of 40. Each of those ones of that major peaks there are roughly at a ratio of about 30,000 from the previous one, 30,000 times larger. So that's saying that if this was a true description of the universe, we would expect to find structures relative to the size of the observable universe. We expect to find something that was about 30,000 times smaller, and then something 30,000 times smaller than that, and so on in the wave structure that it's making. It's dividing, when we pluck a guitar, when we make the second harmonic, the frequency is twice as much as the first harmonic, and the wavelength is half as much. So we're dividing time up, and we're dividing space up in the same proportions of the harmonics. This is a stab at what the universe actually looks like. We've got the Hubble scale, or I'll call it the observable universe size. I put in dark the major features: galaxies, stars, planets, moons. Then I put an X and a Y because there's nothing obvious there: cells, atoms, and nucleons. There are some secondary ones, and we do find that in the prediction as well, that there are often secondary peaks at typically a ratio of 12 from the major peaks, but sometimes other values like 14 or 20, somewhere in that order. And we see the secondary ones. So with the stars, we find there are giant stars that are further apart. With the planets, we find there's the gas giants, which are about the sort of spatial respect, but the terrestrial planets are much closer to the sun and they're smaller. Yeah. And we find that in things we've got bacteria and viruses and so on. And there's, as well as the galaxies, the large spiral galaxies, there's little hangers-on. We've got these Magellanic Clouds, and when we look at Andromeda, it's got them too. And I was talking about that one time, and someone said, yes, they're H2O molecules. And I thought, yeah, we've got this big one here that we live in the Milky Way, and there's these two little ones that are near us. And Andromeda is exactly the same. They are H2O molecules. So you can have chemistry of galaxies, turns out.